Good morning, everyone. I think I have only one announcement, and that is that there'll be a tutorial this Thursday, and it's not a lab tutorial. It'll be a lecture tutorial. So I will go through an example of using condition variables. Last term turned out that students didn't feel comfortable with condition variables because in 252 apparently the focus is on semaphores. So this term I decided to put a tutorial and go through one example on how to use or how to code with condition variables. So that's the topic for this week's tutorial. Okay, if there are no questions, let me get started with the lecture. Yeah, so I got a question. Will all quizzes be true, false? That's a good question. I don't know. Probably not, but maybe. We're just designing quizzes as we go. If at some point we feel like we can have multiple choices, we'll definitely do so. Okay, so just to recap what's going on. So in the previous lecture, we talked about implementing support inside the kernel for threads. So we talked about how we can create a thread, allocate stack, and then yield between the threads. So everything that we talked about, if I were to actually, so I think the most important picture for the previous lecture is this one that explains what's going on with multi-threading inside the kernel. So just to recap, we said we want to have processes with multiple threads. Now, each thread is going to have each user space thread is allocated a user space stack. All of the threads share the entire address space. When we come to the kernel space, the kernel allocates a kernel stack per thread and a TCB per thread and a PCB for the entire process. So that would be the support that kernel provides for each thread and each process. Now, kernel itself could be multi-threaded. It could have multiple threads within it. So for each one of those, so these are kernel threads, you only have one kernel stack and one TCB. And then all the kernel threads share the kernel space. So they have access to everything, each one of those threads. So yeah, this would be the takeaway from the previous lecture. And we talked about how we can actually manage these threads. So yielding from one thread to another thread, creating one of these threads. These are the things, switching, context switching between them. We talked about stop. So that was pretty much what we talked about in the previous lecture. Now, let's move on to talk about a little bit more about user space threads. So that would be the topic of today's lecture, and if we have time, we'll also talk about synchronization primitives. Okay, so in your systems, in your general purpose operating system, this is a snapshot of my Mac 2 years ago. So when I took this snapshot, at that point I had 2,000 threads and 400 processes. This goes to show you multi-threading is basically the approach everybody is taking, and we always, when we're designing operating systems, we have to look at the trends, trends, and provide support for them. Now, multi-threading is everywhere. How can we support multi-threading efficiently? As I described, I think 2 lectures ago when I talked about system calls. So thread create, thread yield, all those functions that we talked about last time. These are services that the operating system provides. And if you remember, the interface is basically system call interface. And if you again remember, we talked about the cost of using system calls. They're very expensive. So as a result, managing threads using operating system primitives could be expensive. Now, you have to make a decision on whether or not this is the way you want to manage your threads, because as you will see in the coming slides, you could actually implement threads in user process, and that's what we want to see. So that this basically sets the stage for saying, okay, good operating systems can provide multi-threading, but if you have a lot of threads and you have to call all these primitives all the time, that's expensive because these are system calls. What else can you do? Okay. So yeah, I talked about these now. We usually context switch in our general purpose systems every 10 to 100 milliseconds. So these are numbers that you have to pay attention to when you're designing your operating systems. The time it takes for each context switch is about 3 to 4 microseconds. If you're context switching between threads within a process, that's much faster, as I described previously. So that would be around 100 nanoseconds. So if you put these numbers together, you can see that the cost of the overhead, so this would be the overhead, the context switching overhead, is negligible, and it has to be negligible. So if you're doing context switching in order of microseconds, then you have a lot of cost here. But if you're doing context switching in orders of milliseconds, then the context switching overhead is low. So when you design your systems, you want to know how long it takes to context switch, and then you want to set the frequencies of context switching to be orders of magnitude higher, so that the overhead cost is low. Now, as we will see later on, if you want to, cases could come up where you might want to context switch between 2 threads that were running on 2 different processes. And that's even harder and more expensive, the overhead of bringing a context of a thread that was running on CPU X to CPU Y, which we'll talk about later on. Again, the overhead is highly coupled with the data that is going to be moved. Basically, how much data are you going to bring to the memory? with your context switching. And again, high level, the amount of data that a process needs to operate smoothly, it's very vague, I acknowledge that, is called working set. So that's basically the minimum amount of data that a process needs to have in memory to run without hiccups. So basically, as this working set size increases, the amount of data that your process needs to process smoothly increases, then the overhead of context switching increases as well. Now, all of that information, basically, I'm going to use that information to set the stage for an alternative way of managing user level threads. So this one is basically what we have talked so far. So for any user thread, so on top of this picture, I have user threads, and the bottom half, we have kernel support or kernel thread. So as I just showed you, there we have basically support for every single user space thread inside our kernel space. Basically, this is the paradigm that we have talked about so far. Now, what exactly this means is that if you want to create a user thread, you create support for it inside the kernel. If you want to context switch between these two threads, you call system calls to yield, for instance, or context switch between the threads. And that's basically what you have in Windows and Linux and Mac and such. So this is a way to go. You have the support, you can use it, and it's fine as long as you don't have a heck lot of threads to manage. Now, the downside of this model is that, well, it's a little bit expensive because you're constantly using system calls. For every single thing that you want to do with your threads, you're calling system calls. Now, solution to that is to manage threads in the user space. What does that mean? So in just to make the case, what I'm going to talk about is having one kernel thread for a whole bunch of user threads. What that means is from the kernel's, from the operating system's point of view, there is only one thread running. So the operating system is going to create only one kernel stack, only one TCB for this thread. Now, inside this thread, in the user space, the user level library can create as many threads as it wants. It can manage it by itself. It has a heap, so it can allocate stack. It can switch between the threads itself. It can just jump from one thread to another thread to another thread, and all of this will be transparent to the operating system. So from the operating system's point of view, this whole thread is just one thread. Inside this thread, the user level library can create as many threads as it wants and can switch between them. So this is very much similar to if any of you have heard of green threads or portable threads. So in this one, now things are a lot faster, because if you want to create a new thread, you don't need to call a system call to create. You can just do a function call because you're inside the user level library. So you can call a function inside user level user space to create another thread. So it's super fast. If you want to context switch between them, you can call it. If you want to yield from one thread to another thread, you don't need to call a system call to yield. You can do a function call. Just remember that bar chart I showed you comparing function calls and system calls. So you're saving a lot by just implementing everything inside the user space. Now, you might ask, So is this the best I can? So should everybody do this? Are there any downsides to this? Well, there are downsides to this. The first one is that what happens if you have a multi-core processor? Now, the entity that allocates cores is kernel. From kernel's point of view, all of these threads are only one thread, and kernel has no incentives to allocate multiple cores to one thread. One thread can get one processor. So what happens is this entire user space thread is going to be allocated, or is going to be assigned to one core. So basically all of these threads have to share that one core. So that's the first downside. So maybe a better way is to put a cap on how many user threads you want, so that you have multiple kernel threads, and each one of them has multiple user threads, so that you can, use multiple cores. But if you put all of your user level threads in one context and get one kernel thread for it, then all of them have to share one core. So that's the first one. The second thing is that, let's say one of these user threads call on an IO. So calling on IO, that means that let's say one of them is calling a system call to read a file. And let's say that file is not ready in the memory. So what happens? So from kernel's point of view, this entire thing asked for IO, because kernel doesn't have any idea how many threads are running inside. So it just looks at, okay, this instruction called IO. Now IO is not ready. I'm going to put the entire thing in waiting. Now you might have actually other threads here that could run, but how does kernel know about them? Kernel doesn't know about them. So all of them will be put into waiting. So that's another thing. So they could all be blocked if one of them is blocked. Now, there are mitigations that you can take. There are steps to mitigate both of these problems. One of the most famous solutions to these sort of problems is using scheduler activations. So these are basically using signals and telling. So basically, what happens is you're going to tell the operating system that don't block me if I call on, if IO is not ready, I can run another thread. Once IO is ready, give me a signal. And then once you get it, so let's say one of your threads call on IO, you can put that one thread to rest, to wait, and start running others, and then tell operating system to give you a signal once that IO is ready. So once you get that signal, you can reschedule the thread that was waiting. So this whole thing would be called scheduler activations. Again, I don't want to go deep into this. I'm just scratching the surface here. If you're interested, there is a little bit of more explanation in the book, but there is a whole lot available in the internet. So if you're interested, definitely look it up. So yeah, so this is basically the alternative to using one kernel thread per user thread. This is a lot cost efficient, and it has a lot less overhead if you can figure out a way to communicate between kernel and the user space library, so that you don't block all your threads when one of them needs IO. And also, if you have a way to load balance your workload on multiple cores, this would be a way to go. And this is very close to what, again, some of user libraries. I'm not quite sure, but I think like something like Go also has a system like this. So it creates user level threads instead of kernel threads. But I'm not quite sure. I myself haven't worked with Go, but that's my understanding of it. So this actually puts everything into perspective. You can categorize kernels based on the number of address spaces they support and the number of threads per address space. So pretty much early operating systems only had one address space, and they could only have one thread per address space. And that would be basically here. MS-DOS, early Macintosh, it was here. Later on, some of them moved to supporting multiple address spaces, but they kept this feature of having only one thread per address space. That would be the traditional Unix systems. You also have this route being taken of having only one address space and many threads. This is basically embedded systems and a bunch of other real-time operating systems. If you wish, the one that you're implementing for labs is also here. So we have only one address space, but inside our address space, we have multiple threads. So we're here, our labs. And lastly, you have this, many address spaces and many threads scenario, which is basically almost everything else, like Linux, Unix, Linux, Windows, Mac. All these systems support many address spaces and many threads per address space. So they're mostly here. Okay, so that's basically the second topic I wanted to cover. Again, we talked about kernel support. We talked about an alternative to using kernel support for every thread, which was, okay, let's just use the kernel support to manage a bunch of threads, and that way we can reduce the overhead. Now, at this point, we're done with supporting, primitives for creating and context switching between threads. Next step. Now, let's assume that you have a multi-threaded system. What are you going to do now? Is everything rosy at this point? Is that all the support that the operating system has to provide just to create a thread and being able to context switch between them? Is that it? And the answer is not really. This is the beginning of a heck lot of other problems that is created when you have multiple threads. So what's the main issue when you have a system with multiple threads? If you have worked with threads, which I think you have in 252, you know that concurrency creates a problem called what is it? Gosh. So when you have multiple threads and they share address space, you have race problem. So race problem is one of the most challenging problems that programmers have to face when they're coding in multi-threaded environments. Now, here is a venue the operating system has to step in and provide primitives so that user space programs can easily do multi-threaded applications or code in multi-threaded application. To do so what we're going to do actually is we want to have threads that can code and share data structures and data between themselves in a safe manner without race problems. So to do so, you saw, this is what you saw in 252. You used mutexes, you used semaphores. You saw a little bit about condition variables. What you're going to see now in ECE 350 is how can we actually implement these? How can we implement mutex? How can we implement semaphore? How can we implement condition variables? So to do that, like always, we're going to get some help from hardware. So different hardware have different support that they could provide. So we're going to see what the hardware gives us, and then we'll use that to implement these synchronization objects. It could just be load and store, very simple load and store that every processor almost provides. We will see how we can actually use enabling and disabling interrupts to implement synchronization objects. And the advanced way of implementing these objects is by some advanced instructions like test and set. So if hardware provides atomic instructions, which I will define later on, then we can use them to efficiently implement synchronization objects. So again, the roadmap started by providing support to create threads, making it optimized, and now we want to let our programmers be able to safely write multi-programmed, multi-threaded applications. And we want to provide primitives for them to have to avoid race conditions and to have mutual exclusion in their codes. So that's going to be the last topic of this lecture. Okay, so we'll start with the mutex. We want to implement mutex as the first primitive that you probably saw in ECE 252. So again, in ECE 252, I assume that you use pthreads, the POSIX pthread, and you used mutex there, but just used it. You probably didn't go deep into how to implement mutex. So this is what we're going to see now. So this is the first take of implementing mutex. So here's a code to implement mutex without any special instruction from the hardware. So all this code does, it uses load and store. So I have two threads here, thread A and thread B. I want to create mutual exclusion. I want, if A enters the critical section, I want B to stay there. And if B enters the critical section, I want A to wait. So that's what this code does. Just to talk a little bit about it, you have two flags, value A and value B. These are two flags. We're going to put them both busy at the same at the beginning. There's also the turn. So for A, turn is set to 1. For B, turn is set to 0. And then we have this while. So this is basically where they're going to wait if they have to wait. And whatever comes after this while is the critical section. Once A is done with the critical section, it's going to turn the flag, its own flag to free. And once B is free, is done with its critical section, it's going to make it free. Now, I'm just showing you the code, and I'm asking you to believe me that this provides mutual exclusion, meaning that if A is in the critical section, B is either done or hasn't entered the critical section. And again, if B is in the critical section, either A is done or A is busy waiting. So Now, this works with just load and store. I provided mutual exclusion, which is basically the task of Mutex, right? So what are the downsides of this? The downsides of this is that it's way too complicated. You have to actually, if you haven't seen this before, you have to sit, study it, run it multiple times with different orders. Maybe thread A runs this instruction first, and then thread B runs this instruction second, and then thread B runs this, and then you context switch to thread A runs this, and then runs this. So there are so many different interlivings of these instructions that could happen, right? And then you have to convince yourself or prove that no matter what the interliving is, the critical section of both two threads are going to be erase-free. So upside, we are not using any special instruction. We're just using load and store. Downside, it's very complicated, and you have to prove that it works. At this point, I'm asking you to trust me that it works, but somebody has to prove that it works. So reasoning about it is hard. The second problem with it is that you don't have symmetry here. You basically look at the turn. So turn is 0 here, turn is 1 here. Look at this while loop. So here you're checking turn to be 0, here you're checking the turn to be 1. Now what happens if you have more than 2 threads? What if you want to have mutual exclusion for 10 threads? So then it even becomes more complicated. Fortunately, it actually exists. So if you're interested, you can look at Peterson's algorithm. So there exists an algorithm that can extend this implementation to multiple threads. But as you can imagine, it's going to be even more complicated than this version, which only has 2 threads. And each one of the threads is going to have its own code. And lastly, which is one of the most important downsides of this implementation, it actually has busy waiting. What is busy waiting? So you will see this busy waiting again and again and again in this lecture. Busy waiting means that when a thread is waiting, it's also consuming CPU cycles. So basically, the thread is still running. It's executing instruction, but it's just stuck somewhere, waiting for something to happen. And where is that exactly happening in this slide? It's basically this while loop. So when, let's say, thread B is here, so thread A cannot enter, and let's say thread A is here. So as long as thread A is running, it will be just executing this instruction again and again and again. This is a branches instruction. It checks, it's a conditional branch. So it checks a condition, and if it's not met, it just executes it again, executes again, until it's met, and it just goes, right? So while A is waiting for B, it actually consumes cycles. So it's busy waiting. It's executing instructions while waiting. Compare that to, let's say A just checks this. It says, oh, I cannot go. Let's wait for this by changing the state of thread A to busy, sorry, to waiting. So basically saying, okay, thread A, you're now waiting, meaning that you're not going to be consuming instructions anymore. Your state is not ready. Your state is not running. Your state is waiting. And then later on, once B is done, somehow B sends a signal to A, wake up, now it's your turn. And then what that means is, let's now turn the state of thread A to ready, and then eventually it will be scheduled and it will be executed. So with this implementation, with this alternative implementation, A is not busy waiting when it doesn't have the CPU, when it's waiting. So it's just put in a waiting state and it's not being scheduled. So we prefer that, the second implementation, to this implementation, because this is wasteful. Basically, A is using CPU cycles and not doing anything. So let's improve this. Let's see what else we can do. What are other implementations of Mutex? So the idea is, well, let's focus on uniprocessors for a bit. Later on, we'll talk about multiprocessors. But let's say we have a uniprocessor. If thread A is running, how can thread A stop running? Well, we talked about two ways of, context switching. Two events that cause context switching. One was a voluntary context switching, and the second one was involuntary context switching. In the voluntary context switching, thread A yields the processor, says I'm done, I don't want to use the processor anymore. In the involuntary way, an interrupt happens. So something happens, an interrupt happens, and the context switching then after that happens. So if I want to have mutual exclusion, meaning that if I want A to run something without being kicked out and and another thread coming in, I can just prevent both of these two. If I prevent both of these two in a uniprocessor, then I by definition get mutual exclusion, because the moment A enters the critical section, if I disable both of these two, then I'm sure that A can finish its critical section without being interrupted, without us, the moment you start the critical section, you're not going to be paused, and then we would context switch someone else who would then be able to get to the critical section. The moment you start your critical section, it's guaranteed that you can finish your critical section and get out. And while you're in the critical section, nobody else can be in the critical section because we only have one CPU and you're not relinquishing that CPU. So how can we actually do these two? How can we disable these two in a uniprocessor? So the voluntary one is easy. Well, don't call yield. When you enter your critical section, make sure that you don't call yield. You don't exit, for example, right in the middle of your critical section. So don't do any of those. Don't relinquish the processor. So that's easy. What about the involuntary one, like interrupts? Well, you can disable interrupts. Interrupts you can disable them. Should you care about exceptions or system calls? Yes, you should, because they could also cause context switching. But that's easy because they're synchronous. So exception, don't cause any exceptions. Don't divide by 0. Don't do any of those because they are in your control. So let's say we write a code that doesn't cause any exception. What about system calls? Well, don't call any system calls. So that way you pretty much set the stage for a thread to not be interrupted when it enters its critical section. And that's basically what we want to do. And this is how you would implement it in a naive way. So here is now moving from implementation take 1 to implementation take 2. I'm going to give it some form. I'm going to use some C++ stuff, but it's just pseudocode. So let's say this is class Mutex that I want to implement. So it's going to have two functions, two members, public members, lock and unlock. So with lock, I just disable interrupts, and with unlock, I enable interrupts. So, and then I'm going to use this lock and unlock at the beginning and end of my critical section. So this should give you a signal when I say naive implementation. So this is going to work, but there are downsides to it. First, let's talk about upsides. It's actually, it's simple, right? It's just one line of code, disable interrupts, and you're going to be fine. And then for unlock, enable interrupts, and you're going to be fine. Although you have to make sure that between lock and unlock, you don't cause any exceptions, you don't call any system calls, and you don't yield the processor. Well, that's a system call. So if you don't do any of those voluntary ways or synchronous ways of relinquishing the CPU, then this should give you mutual exclusion in a uniprocessor. Now let's talk about downsides. First of all, you cannot let users use your mutex. So you wrote your class mutex, but user processes cannot use it. Why? Why can't user processes use mutex lock? Well, what if a user process does this? Mutex lock while true. What's going to happen in a uniprocessor? So what does this do? The first line is going to disable interrupts, and then line 2, you're going to have an infinite while. So now there is no way for the kernel to take the control back, and your system will be stuck now in this while loop. So we don't want to let users be able to do this. And with this implementation, this could happen. So as a result, we don't want users to do this. So we're not going to be able to let users use this class mutex. What about multiprocessors? Would this work in multiprocessors? The answer is not really. And the reason is, when you disable interrupts, interrupts are going to be disabled on only the processor that calls disable interrupt. So you have one processor that is not interruptible, but then other processors, they could be interrupted. So if you have multiple threads, then they could be running on the other processors, and they could enter the critical section while you are inside the critical section. So there's no mutual exclusion. That's the second downside. And the last downside is basically related to real-time systems. When you disable, there is no guarantee on how big or small critical sections are, right? Even if you don't have this situation that you write a while loop inside your critical section, making your critical section be infinite. But again, like, your critical section could be big. You could be doing a lot of stuff inside your critical section. And when you disable interrupts at the beginning of it and enable interrupts at the end, everything in between is uninterruptible. So the moment one thread enters the critical section, the system is all locked down for that thread. Now, what if something emergency happens while one thread is inside its critical section? Well, operating system cannot deal with that situation because interrupts are disabled. Let's say if you are writing a operating system for an embedded system that is going to, be deployed in a nuclear site or in a car, in a self-driving car, or you name it, mission critical systems, then basically you impaired yourself by allowing threads to disable interrupts for a long period of time. So that's basically what you don't really want to do. That's why we actually called it a naive implementation. It works, it has the merits, but it's not going to work efficiently. So now, in the coming slides, we'll take other turns to refine this so that we can address all of these issues that I just raised with this implementation. So what time is it? Okay, let's have 2 minutes of break and then I'll continue. Okay, so here's take 2.5. We're going to still use disabling interrupts, but we want to minimize the time that it takes for us to keep the interrupts disabled. The way we're going to do that is we're going to introduce a local, a lock variable, sorry, a lock variable, and then we'll use disabling interrupts to just modify this lock variable. And then we enable the interrupts again back. So the time that it takes for us to disable interrupts is going to be really fast, really short, because the only time that we're going to use disabling interrupts is to change the value of this variable. Here's the implementation. So here is our class. So class Mutex. We're just refining the implementation that we saw previously. This is the variable, value free. Initially, it's free. We're going to introduce a queue, waiting queue. So this is a member of class Mutex that we're going to put every thread that wants to wait while this Mutex is locked in this waiting queue. And then it has two lock and unlock functions. Let's look at the lock implementation. So the lock implementation, let me just get it all down, and then we'll talk about it. Okay, so let's look at the lock. So at the beginning of it, I'm going to disable interrupts, and I'm going to check the value. If the value is busy, it means that the mutex is locked. So I have to wait. To wait, I'm going to make the state of my thread to waiting. This is what I was describing before. So I don't want to busy wait. So I change the state to waiting, and I basically context switch to someone else. Right? I choose another thread and context switch to that other thread because I cannot go further. I need this mutex, and the mutex is locked, so I'm going to be waiting. So here I context switch to someone else. If you remember, this thread switch was like you get into it with one context, you get out of it with another context. So sometime later on, I'm going to wake up. So the next code that is going to be executed after this line is after I wake up, I will change my state to running. Now, this was the if the lock is busy. If the lock is not busy, I make it busy and I enable interrupts. So as you can see, the amount of time that I disabled interrupts and enabled interrupts, this is independent of the length of my critical section. So the critical section that this lock is going to protect has nothing to do with the time it takes for me to disable interrupts. I'm only disabling interrupts and enabling them back to just change the state of the mutex. Now let's look at the unlock function. So unlock also disables interrupts and enables interrupts at the end. What it does, if you're unlocking, you check to see if anybody is waiting. So if this waiting is the queue of the mutex, right? It was the element of the mutex. Here we added this thread that wanted to wait to this waiting queue. So you just check, see if anybody is there. If nobody is there, so if this is here, then you just make the value free. If somebody is waiting, you don't change the value because the value is busy. You keep it busy. You don't want to turn it to free because you're going to wake up someone else. It's kind of like those, anyways, I have an example, but I just don't want to get into it. But anyways, so you just wake somebody else up and keep the lock busy. So they would wake up here. And as you can see, they're not also going to change the value at all. So the one who is going to wake up here will just make their state running and they exit. So they also don't change the value and the value remains busy because it was busy, somebody had it, and then somebody else now has it. So the value doesn't change. And that's all you do. So you remove the one that you want to wake up from the waiting. You make their state ready. This is important. You're not going to make them run right away. This is something that we always ask in the quizzes, and people sometimes make mistakes. So we're not going to run them right away. We just make them ready and put them in the ready list. So at some point, they will be scheduled. And whenever they get scheduled, they start running from here. Yeah, sure. So somebody's asking about this implementation. They want a second overview. I will give another overview. So what if a thread waiting on the lock blocks, but then some other arbitrary thread voluntarily releases and the blocked thread runs again without the lock having been released? Yes, so that couldn't happen, right? If somebody so interested of changing, and so instead of changing mutex value, we're basically passing a button for another thread to run. Yeah, that's exactly what the example I wanted to mention. And I did not know the terms of that example. Thank you for mentioning it. Yes, so an overview again of this implementation. So we're using interrupts, disabling and enabling interrupts only to change the state of the mutex. What is the state of the mutex? Basically the value and the queue. So if I don't actually want to go in the previous slide, but it had two elements, value and the queue. So every time I want to change these, I disable interrupts. I change them and then I enable interrupts. That way, the time that interrupts are enabled or disabled is independent of the critical section that this lock is going to protect. That's the first point. The second point, here in the unlock case, if I want to unlock, I just look at the waiting queue, see if anybody else is waiting. If somebody is waiting, then if somebody is waiting, then I would just take them out of the ready list. I remove them from the waiting list. I make their state ready, and I just get out of this unlock. they will eventually be scheduled. Whenever they get scheduled, they're going to wake up from here after this thread switch, and they're going to make their state running. And I did not release the lock, so they will have the lock. And nobody else can get the lock, right? If somebody releases the lock here by calling unlock, and somebody else is waiting in the queue, then the lock is not going to be released, so nobody else can come and lock the mutex again. Hopefully that answers the question. So I guess I explained this. Now, the only time that the interrupts are disabled is basically whenever I want to change the state of my mutex, and that's it. So I could have a really long critical section, but I'm not going to disable interrupts for that long. It's going to be just disabled during the time that I'm changing the state of my mutex. Yep. Okay. Now, let me talk about one more important thing, and that's re-enabling interrupts. So look at this lock implementation that I just showed you. At the beginning of it, we're going to disable interrupts, right? And then let's say that the lock was busy. So we're going to get into this if. Now, at some point, I'm going to call this thread switch. So I'm going to go to sleep and then context switch to someone else. Now, the question is where and when should I enable interrupts? So I'm disabling interrupts and going to sleep. What's going to happen to the interrupts? So should I enable interrupts here? The answer is no. If I enable interrupts here, then somebody else could call unlock. So if I enable interrupts, I basically open the door for someone else to be scheduled. And maybe that someone else that is going to be scheduled is the one who is going to unlock the mutex. And if they do so, I still haven't added myself to this waiting. So they will release the lock, thinking that nobody's waiting. And then again, when context switch happens and I'm scheduled, I'm going to go to sleep, not knowing that the lock was released. So this is not a good place to do it. What about here, right before I go to sleep, right before I do I call thread switch? Is this a good place to do so? No, not really. It has almost the same problem. The problem is, if I, at this point, let's say I unlock, let's say I disable, I enable interrupts, and then let's say another thread is the one that wants to unlock the mutex is a schedule. It checks the waiting and it sees that I'm in the waiting queue. So it says, oh, okay, I'm going to give the lock to you and I'm going to wake you up. So I just made my state to waiting. That the thread that is calling unlock will make my state to ready. And then I will be scheduled again. What happens when I'm scheduled? I'm going to go to sleep right after that, because the next line I'm going to execute is this thread switch. So I'm going to go to sleep again. So instead of me going to sleep completely and then waking up so that I can start running from here, I start running from here and I go to sleep again. So again, something bad will happen. So then what should I do? Where should I enable interrupts if I'm going to go to sleep? The answer to that question is you should enable interrupts by someone else, not yourself. So we'll make this as an invariant in our implementation. So what is that invariant? The invariant says we have to make whatever thread that is going to run after it wakes up, the first thing that they have to do, or one of the things that they have to do, is to enable interrupts. So any thread that gets scheduled, they have to enable interrupts when they get scheduled. So here is the example. So you disable interrupts, thread A disables interrupts and calls thread switch. At this point, a context switching is going to happen. So I'm going to make thread B to enable interrupts after it comes out of its context switching. And then at some point, this thread B is going to disable interrupts and call thread switch. And then I'm going to come back to thread A from this thread switch, and thread A is going to enable interrupts. So in this way, this is our invariant that we will have to implement everywhere in our kernel. And that says basically every time you wake up, you're scheduled, you have to enable interrupts. The one place that this becomes important is when the thread is for the first time scheduled in the stub. That's one of the items in the housekeeping that you should do. Enable interrupts. That's the first thing that you should do when you're scheduled. You have to enable interrupts. I got a question. What if you thread switch to a while1 thread, which never returns, leaving interrupts disabled? That wouldn't happen, right? So the while part is going to be inside the user code. The enabling and disabling interrupts is going to happen inside the kernel code. So as a kernel developer, we have to implement this. So if I go back to this code that I have here, you will see that this invariant is indeed implemented. So here I disable interrupts and I context switch. Whenever I come back from this switch, I make my stage running, and the next thing I do is I enable interrupts. So again, at this point, after this is done, this is inside the kernel. I might go to the user, and there might be a while loop, but that's fine. As long as I don't have that while loop inside kernel, it should be fine. Right, so okay. Okay, so what are the problems with this take? It's the main problem with this is that this is an implementation only feeded for operating system. So this lock could be only implemented by the operating system. The reason for that is that it executes enable interrupts and disable interrupts in the lock and unlock functions. And disabling and enabling interrupts are privileged instructions. So you cannot let user code enable or disable interrupts. Therefore, this implementation is only suited for kernel libraries. So this is a lock that could be implemented by kernel. This lock, this implementation cannot be done by user processes because they cannot enable or disable interrupts, basically. The other problem with it is that, very similar to the take 2, we still haven't dealt with multiprocessors. So every time that you use enabling interrupts and disabling interrupts as a mean to create some mutual exclusion, it only works in a uniprocessor system. Because in multiprocessor system, you might disable interrupts on one core, but the other cores can still run, and you still could get race conditions. Alternative solution is to use atomic read, modify, write instructions. So these are special instructions that do multiple things. So far, the only instructions that we were thinking about were load and store, and then enabling and disabling interrupts. Now, what if hardware can provide other instructions that do some more advanced stuff for us, like read, modify, and write at the same time? So these instructions they happen atomically. What that means is they read, they modify, and write to a memory location at the same time. So basically, no other instruction can interleave between these three tasks. So it doesn't happen that you read and before you modify, another instruction from another thread can be executed. So read and modify and write happen at the same time. Now these are examples of read, modify, write instructions. So this is basically just showing you the logic of these. It's not actual implementation. So for instance, test and set. Given an address, I want to read what is in that address. So this is read. I modify that, and then I save it. This is basically modifying and saving it, and then returning the result. Again, this is the logic of what test and set is. So it just tests the address and sets it to 1. So no matter what it was in this address, it's going to be eventually 1, but you will get to see what it was before you turn it to 1. And this is actually not the way that it's implemented. So this test and set is one instruction that hardware implements. So basically, when it fetches this instruction, it identifies that this is a test and set instruction. If you remember the fetch, decode, execute, and save. So when it figures out that this is a test and set instruction, the hardware does all 3 of these together before it executes any other instruction. So that way, you're sure that this instruction happened atomically by itself without any interleaving with any other instruction. Again, and this is just a logic. The other one is swap. So I give a register and an address in memory, and this instruction, again, another load, store, load, modify, store instruction. It just reads that address, change the value in that address to this register, and then swap the value of register with whatever was stored in that address. And the last one is compare and swap. So I give it 2 registers this time and an address. It first checks if the value in that address is equal to register 1, then it turns the value to register 2 and returns success. And otherwise, it returns failure. So if in this address there is anything other than register 1, then this is going to return failure. But if it is register 1, then it makes it register 2. So it first compares and then swaps. Now, let's use these instructions to implement logs. I think I have 10 minutes left. Okay. I'm mistaken, right? I have 10 minutes left. Okay. So I'm going to use this is basically using test and set as an instruction to implement logs. This is a happened. Yeah. So I'm going to create this class spin log. It has only one element, the value, and it has 2 public functions, lock and unlock. This is very similar to take 2, the first one that with Mutex. So let's see how it works. Okay, so with the lock, in a while, I run test and set with the value, and in the onlock, I make value 0. So what is this doing? Well, if the value is 0, what does this test and set make it? Test and set will make the value 1, but then returns 0. And this while, if this is 0, it just gets out. It doesn't do a while. So the first one that executes this lock will turn this value to 1, and this lock basically makes this value 1, and then exits. So then whoever called lock is now inside the critical section. Now, later on, if somebody else calls lock, they're going to execute test and set. The value is 1 now. Test and set will make it 1 again and returns 1. And this while will keep doing it again and again and again and again, right? So they will get stuck here. If the value is 1, whoever calls lock will get stuck here. And later on, the first one who locked this spin lock will call unlock. At that point, the value becomes 0. Now, the moment the value becomes 0, one of the ones that are now waiting on this while will see this value turn to 0, because this test and set returns the value, and it sets it to 1. So that particular thread that sees this value set to 0 for the first time will be the winner. So they would now lock it and get out of the lock function. So at any given time, only one thread can get out of this lock, and other threads will just spin lock there. That's why we call this a spin lock. So I got a question. Wouldn't it make more sense to say that an atomic read modify instruction execute as one instruction? It is, yeah. Isn't that the definition of atomic? Yeah, it actually runs as one instruction, but that one instruction does multiple things. So sorry if my explanation wasn't clear. It is this test and set is just one instruction, but it just does multiple things, and it's all done in hardware. So hardware provides this instruction as an atomic instruction. So it's just one instruction with multiple functionality. It does multiple things for us. Okay, so yeah, we explained these. What is wrong with this implementation? It's the things that are wrong with this implementation. The main thing is basically busy waiting. So any thread that is waiting for this value to become 0 will be just executing this while loop, and that's very expensive. So this is busy waiting. So that's the main drawback of this implementation. Now, what are the upsides though? The first one is that, well, the machine can still get interrupted. We didn't use interrupts. We didn't disable interrupts. We didn't enable interrupts. We didn't have to deal with any of those. That's a plus. Second, you can actually make the user space library implement this lock for themselves, because you're not using any privileged instruction like disabling or enabling interrupts. I got a question. Is spin lock busy waiting? Yes. So it is busy waiting. The third upside is it works on multiprocessors. The reason for that is that we're not using any, enable interrupts or disable interrupts. So you can actually you can use this in a multiprocessor. The core that executes test and set first will lock the spin lock, and any other thread that is running on other cores that run next, they will just wait. I got another question. How does enabling and disabling interrupts work if we are managing more than one mutex lock at a time? Yeah, so if you're asking, managing more than one mutex lock at a time. I'm not sure if I follow that question. Can you explain more what you're asking? Okay, so those are the upsides. The main downside of this is busy waiting, right? So any thread that is waiting is going to be busy waiting, and that causes priority inversion. I'm not going to talk about this in details, but this is I have a lot of slides for it later on when I talk about real-time system. So priority inversion can happen. So I'm just mentioning it here. I will come back to it later on when I talk about scheduling. So in essence, it could happen that some high priority thread gets to busy wait while a low priority thread holds the lock. And that's pretty much the essence of it. Again, I will explain it in more details. So just keep in mind that priority inversion could happen with this implementation. So busy waiting, bottom line, is bad. We have to solve the problem. How do we solve the problem? This is implementation of Mutex take 3. I'm going to use spin lock to implement Mutex. And this is how I do it. I'm going to have class Mutex have 3 elements in this time: a value, a spin lock, and a queue. So compare this to take 2.5, where you had a value and a queue. Now I added a spin lock to my Mutex, and again the same 2 functions. Now I'm going to add a. Oh, I only have 2 more minutes. I'll see what I can do. So I'm adding a class scheduler to just make things tidy. So this class scheduler has a ready list, and it has its own spin lock, and it has 2 functions: suspend and make ready. Now, these spin locks here, this spin lock in class scheduler and this spin lock in Mutex, we're going to use these spin locks whenever we want to change the state of our Mutex. Very similar to what we did with enabling and disabling interrupts. So here's how we do. Let's just do lock and unlock. Very, very similar to what we did with interrupts. So instead of disabling interrupts and enabling them at the end, I just lock my spin lock. I do exact same things. I check the value. If the value is busy, I add myself to the waiting, and I suspend myself. So I call a scheduler, and I suspend myself. I pass my Mutex to the scheduler so that the scheduler can make it free. Because at this point I locked it, and I'm going to sleep. So this time I'm going to ask the scheduler to unlock this spin lock. Else, if the value is not busy, then I make it busy and I unlock the spin lock. And here's the unlock. Again, I just lock the Mutex. I check if anybody is waiting. If somebody is waiting, I remove them, and I call the scheduler to make them ready. And that's it. Because when they wake up, they are not going to change the value to busy, so I don't make the value to free, basically transferring the lock to the next one. And else, if nobody is waiting, then I just make the value free, and then I unlock the spin lock. Now, with this implementation, this is where I'm going to end this lecture. With this implementation, I addressed the busy waiting problem as well. Because I now have this waiting queue, I don't want my threads that are waiting for this lock to busy wait. I just put them in this waiting queue. I still have busy waiting here in this lock because this spin lock has busy waiting, but this busy waiting only happens for a short period of time when I'm actually when one thread is changing the state of the mutex. So busy waiting is basically unavoidable in some sense in this implementation. So we're just shrinking the time that a thread has to busy wait. So the only time that the thread is busy waiting is when they're just waiting for this lock, for the mutex's spin lock to be free. And once they get in, either they run or they get suspended. So the busy waiting ends. Okay, so we'll continue from here on Thursday. Thank you so much. Take care, be safe. Talk to you on Thursday. Bye-bye.